Okay, I got an email asking for a little bit more clarity on section 1.8 in your book. So I just wanted to kind of run through some of the topics in 1.8 again. First, what we care about is operations on functions. And essentially the idea is, at this point, I know that I can have some function y equals x squared plus 2, but writing in function notation, I can write f of x equals x squared plus 2. And we understand that if I want to find f of 3, I just replace the x with a 3, and I get 3 squared plus 2, which is 9 plus 2, 11. And we want to get used to using this function notation right here and messing around with it, as opposed to always just using y. But the way it kind of works in math is, once you define something, in this case a function, f of x, then the question becomes, what can you do with functions? When I define numbers, once I define them, then I say, what can I do with them? I can add them, I can subtract them, I can multiply and divide them. Once I jump from, say, integers to fractions, I still say, can I add them? Can I subtract them, multiply them, and divide them? What are the rules? How do things change? If they're integers that I'm adding, I can just add like normal. If they're fractions, I have to find common denominators and stuff like that. But essentially, from a math perspective, that's what we do. We define something, there's a function, then I say, good, now what can I do with functions? So, if we have, say, f of x equals, we'll use that, x squared plus 2, and g of x equals 3x minus 5, I don't know. Now I have two functions. Now I just want to run through all the operations I would do with numbers. So if I had f of x plus g of x, adding functions, what would I get if I added them? The good thing is, I can just directly substitute. In the same way that here I substitute and I replace the x with a 3 to solve it. F of x plus g of x is just f of x plus g of x. So I get f of x, which is x squared plus 2, plus g of x, which is 3x minus 5. And you don't need the parentheses here, but I'm doing them deliberately for the other stuff we're going to do. Now just combine like terms. There's an x squared, there's a 3x, then I have a 2 minus 5, which is negative 3. If I want to subtract functions, f of x minus g of x, and here the parentheses are important, I do the same thing, x squared plus 2 minus 3x minus 5. And here again, just remember, now I'm subtracting the whole function, so I have to make sure to distribute that negative in. But I still do the same thing, combine like terms, x squared, now I have a negative 3x, 2 minus negative 5 is 2 plus 5, because the two negatives cancel, which is 7. That's addition and subtraction. Next up, I can do multiplication. But again, all I do is substitute. F of x is x squared plus 2 times g of x, which is 3x minus 5. Now I say, that's just multiplication of binomials, FOIL. X squared times 3x is 3x cubed. X squared times negative 5 is negative 5x squared. 2 times 3x is 6x. 2 times negative 5 is negative 10. I can combine like terms, but in this case, nothing will combine them good. And there's a point here, I'm not actually doing anything different. Addition of functions, write out the functions. To add them, just do what I would have done at the beginning of the semester. Combine like terms. Subtract them, write them out and subtract them. Combine like terms, just make sure to account for distributing the negative in. Multiplying them, if I saw this without knowing they were functions, I would say FOIL that, which is exactly what we do. So there's nothing new here, it's just a notation that looks new, but we're doing things that you already know how to do. The last operation is division, but again, I just write it out. F of x, which is x squared plus 2, over g of x, which is 3x minus 5. And then that one, I'm done. I don't have to do anything else. The only trick that comes up here, when we originally defined functions, we said if we define a function, then we care about the domain and the range. We actually don't worry about the range unless we're graphing it. But as far as the domain goes, once we define a function, that's important. And we had our rules for determining what's the domain of a function, what causes problems. But the only two problems were either a fraction with an x in the denominator or a radical with an x inside of it. Same idea here. Now that I'm defining this new thing, it's called the sum of functions because I'm adding two functions together. This is the difference of functions because I'm subtracting two functions. I'm creating a new function right here, and so on. But now all I do is go back to my old rules. Look at this. What's its domain? No radicals, no fractions. The domain is all real numbers, negative infinity to infinity. This one, no fractions, no radicals, negative infinity to infinity domain. This one, no fractions, no radicals, negative infinity to infinity. So again, we know the rules to find the domain. I just apply those rules to the new function I create. Here there will clearly be a problem. I have no radicals, but I do have a fraction with an x in the denominator. So we just go to our rule. Take the denominator and set it equal to 0. Add the 5, divide the 3. We get x is 5/3. That's the x that will make the denominator 0. So that's the x I don't include in my domain. So my domain will be negative infinity to 5/3 open, union 5/3 to infinity. And again, I stress, we're not doing anything new. We're doing exactly what we did when we defined functions in their domains. Only now, we start with a couple of functions, manipulate them, and then do all my same rules for the new thing that I've created. One thing that we do go over, which admittedly is not incredibly important for this class, but it's a lead-in to what we'll do in calculus, for those of you who go on to calculus. We have what's called the difference quotient. It's really important in math and in calculus. And all it is f of x plus h minus f of x over h. And all you do is plug in and then algebraically simplify. But if I have a function, we'll use that one. F of x equals x squared plus 2. Find the difference quotient for that f of x. All I do is plug in. By definition, f of x plus h, I replace the x with x plus h. So I get x plus h squared plus 2. And I'll put this in parentheses so we can see it. That's f of x plus h. X plus h squared, because I replace the x with x plus h, then square it, plus 2. Minus f of x. That's f of x, just plug it in like we were just doing with that other stuff. All over h. That's it. Now just do the algebra to simplify it. So here, there I have to FOIL, and all of you know how to FOIL, so really quickly, you'll get x squared plus 2xh plus h squared plus 2. Now distribute the negative, minus x squared minus 2 all over h. And again, keep simplifying. And here, x squared minus x squared, 2 minus 2, and I'm left with 2xh plus h squared all over h. On top there's a common h, factor it out, and I'm left with 2x plus h over h. Now there's a common h on top and bottom, and I'm left with 2x plus h. And that's my answer. And one tip that I would point out, when you do this difference quotient here and plug in and do all the algebra, you can tell if you're doing it right if at the end you factor an h out of everything on top, like we did here, and then cancel the h on the bottom. that's kind of how this difference quotient works when we algebraically manipulate it. So if what you have, you don't get this cancellation of h's right here and end up without a fraction because this h disappears, then it means your algebra is not correct up above that, so go check it. This does not happen for every single difference quotient, but for all the ones we are doing, it definitely will. So you can use that as a guide. If you plug into this, it has to algebraically work out that you can factor a common h out of every term on top, and then cancel that h top and bottom. So just keep that in mind. Okay. The last part of this section, this 1.8, was composition of functions. And we say f circle g of h. You literally just say circle because it's a circle. F circle g of x, which by definition is f of g of x. And that's it. And keep in mind, as I mentioned in the other videos, assuming you watched them, g circle f of x is g of f of x. The order that I write those does matter. In general, those are different. Sometimes they end up being the same. That's a special case that we'll check out later in the semester. But in general, that's not true. And the order that matters. F circle g is f of g of x. G circle f is g of f of x. But ultimately, this is just an algebraic exercise like the last few we did. That's kind of why they're all grouped together in this section. Meaning, suppose I have, f of x equals x squared plus 3. G of x equals 2x minus 5. Now down here, I want to find f circle g of x. By definition, that's f of g of x. Now do what I did before. Order of operations says I start on the inside of the parentheses, so I start in here. Substitute. Replace g of x with what g of x is. So that's f of 2x minus 5. I replace g of x with g of x. Now, apply f to that. What does f do? It takes whatever you plug in, squares it, and then adds 3 to it. Now I'm plugging in 2x minus 5. So I take 2x minus 5, square it, and add 3 to it. And again, you just kind of have to get your brain to see this is really x squared plus 3. But my x this time is 2x minus 5. So I replace the x with 2x minus 5. But everything else is identical. If you want, I'm not going to take the time here. You could FOIL this out and then combine like terms. For this, I'll just leave it like that. But then, I can find g circle f of x. You can also say g composed with f, because it's a composition. I just like saying g circle f, because that's how we said it when I was in school. G circle f of x is g of f of x. Same thing. Now I start in the parentheses. I replace f of x with what f of x is. X squared plus 3. Now, apply g to that. What does g do? It takes whatever you plug in, multiplies it by 2, and subtracts 5. This is what I'm plugging in. So I multiply it by 2, then I subtract 5. And again, g of x is 2x minus 5, 2x minus 5. Only now my x is this thing. But it's the exact same. And the good thing with compositions, if you want to practice, you can pretty much just make these things up however you want. You can do g circle g of x. Because automatically, that becomes g of x. Now I do the same thing. That is g of x. Substitute, that's 2x minus 5. Now apply g to that. What does g do? It takes whatever you plug in, multiplies it by 2, and subtracts 5. So that's what I'm plugging in. I multiply it by 2, and then I subtract 5. And again, you should see the similarities here. Both of these had g applied to them at the end. 2x minus 5. 2x minus 5. But for this one, this was my x. For this one, that was my x. But they end up the same, up to the fact that I could distribute and then combine like terms that look different. But in principle, 2x minus 5, 2x minus 5. The x I plugged in was different. Last one, just to do one more example. What if I have f composed with f of x? Again, that is f of x by definition. Now, I replace f of x with f of x, which is x squared plus 3. Now apply f to it. What does f do? It takes whatever you plug in, for us x squared plus 3, squares it, then adds 3 to it. And again, this one and this one look the same, where we apply f at the end. Something squared plus 3. Something squared plus 3. The something that gets squared is just what I plugged in. This should hopefully give a better understanding of compositions and function operations and all of that. If you need more examples or want me to go through homework problems or whatever, feel free to email me or let me know, and I'll make another video going through those. It's not a problem. But hopefully this, with a bunch more worked out, will help make it clearer.